Hi, I'm Thuecks, an associate professor here at Washington College, and I'm going to talk to you about plasma physics. This is my field of research, my field of expertise, and I'd like to introduce you to what plasmas are, how plasmas are generated in the lab, and how plasmas can be useful to us in life. So plasma physics is often thought of as the fourth state of matter. This is a state of matter just like the states that we typically encounter in our everyday lives, notably the solid state, liquid state, and gaseous state. Typically, in order to transition from state to state, we need to add energy to a substance. So if you imagine a pot full of ice or solid water, solid H2O, we can place that pot of water onto a stove heating element. If we turn on that heating element and start adding energy, basically heating up the ice, that ice is going to experience a phase transition, converting from solid to the liquid state. If we continue that process, that liquid water is going to start vaporizing or turning into steam, the gaseous state of water. Now, if you can imagine adding even more energy to that water, even more energy to that gaseous state, we can take that gas, which is typically made up of a large number of neutral molecules, and we can start breaking apart those neutral molecules. We can start stripping off electrons from those neutral molecules, and we're left with this kind of gas-like state that's made up of free-floating negatively charged electrons and positively charged protons floating around. This plasma state shares a lot of similarities with gases, but it's a lot more challenging and a lot more interesting. Plasmas, unlike gases, are very, very hot. Plasmas typically run on the order of millions of degrees Fahrenheit, so extremely hot. And plasmas are electrically conducting, meaning that they can conduct electricity through them, unlike a neutral gas. Since these plasmas are made up of charged particles, these electrons and positively charged ions, they can also have their behaviors influenced by the presence of electric and magnetic fields. Let's talk about how we can make a plasma in the laboratory. Pictured here, we've got basically a vacuum chamber. This vacuum chamber is going to be filled with some type of gas. In the example that I have pictured here, we're using neutral helium gas. So you can see one example helium atom here, where we've got a nucleus that has 2 protons in it, so it's positively charged twice, and it is surrounded by a cloud containing 2 electrons, which are each negatively charged. Hence, the molecule as a whole has no charge associated with it. So we're going to fill up our vacuum chamber with a large number of these helium gas molecules. We're also going to place 2 metal plates into the vacuum chamber on either end. So one of these we're going to call the cathode, and one of these we're going to call the anode. So what we're going to do then is use a power supply to apply a large voltage between the cathode and anode. Now, the presence of that voltage difference and separation leads to an electric field that exists between the anode and the cathode. This electric field can apply a force onto any charged particles that might be present in that background gas. Now, we may have filled the chamber with neutral helium, but things like interactions with cosmic rays can produce a very small number of free electrons that are free to float anywhere within the chamber. So, we've got primarily a neutral gas with a small number of charged particles, a small number of electrons in there. That electron is going to be accelerated to higher and higher speeds from the cathode toward the anode. Eventually, that electron is going to collide with one of these neutral helium atoms. If that electron collides with enough energy, violently enough with that neutral atom, it can knock an electron off of the neutral atom. Once this happens, we now have our original electron and our new electron that's been knocked off of the helium atom. So these 2 electrons are now accelerated again by this electric field that's present. And they are free to potentially collide with yet more neutral helium atoms. At the same time, what's left over of that original helium atom is now positively charged because it's missing an electron. That positive charge is going to be accelerated by the electric field in the opposite direction. So we see here that the two electrons now collide with two more helium, neutral helium atoms and knock off further electrons. So we're going to go from 2 electrons to 4 electrons that are now free from the helium atoms. And all of these what remains of the helium atoms are now all positively charged and are going to move toward the cathode. Eventually, those helium ions collide with the cathode wall, this piece of metal that we call the cathode. That collision is going to result in the release of yet more electrons into our volume. And those electrons are now free to also be accelerated and collide and so on and so forth. So what we see here is a chain reaction that occurs. We start with just a single free electron, but via collisions and continual acceleration of these charged particles, we slowly build up a large number of free electrons and also these free ions, these free positively charged particles. This is what we call an ionized gas or a plasma. So we've gone from a single free electron to a large number of charged particles, almost completely charged particles in this volume. All right, so here I'm going to generate a plasma for you. This is using one of the pieces of apparatus that we use in our advanced physics lab class. So students will do a few weeks of experiments on this, on plasma physics using this apparatus. So this is going to be the same type of setup that I was talking about just a minute ago. We have this tube that we're going to basically put under vacuum. That may be the sound that you can hear in the background. We want very little gas to be in there because we don't have a lot of energy that we can provide. So we only have enough energy to basically turn a small amount of gas into a plasma. So we've got the vacuum pump to bring this to a much lower pressure than atmosphere. So for right now, for instance, right now we're at 393 millitorr. This compares to atmospheric pressure, which is 760 torr or so. Inside this chamber, we have our cathode and anode plates. So we have our cathode plates over here, and we have our anode plate over here. And they're connected to rods, which I then connect to a power supply, which is here. This power supply can apply several hundred volts or up to 2 kilovolts of a voltage differential between those two plates. So it'll be, over the course of about 30 centimeters, up to 2 kilovolts difference between them. So what I'm going to do is turn out the lights, and I'm going to start turning up the voltage until we get a plasma. Okay, so we're turning up the voltage. This number is in kilovolts. So right now we're at about 120 volts between the two plates. We should get a plasma shortly. We just passed 1 kilovolt, and there we go. We have our plasma. So this plasma is showing up as basically a dim glow. It's much more visible when we have it at dark like this. So what's happened is that chain reaction that I was talking about happens very, very quickly. You saw the plasma appear almost in an instant. And then once it's there, it's self-sustaining, or it's easy to keep present. The light that you see being emitted from the plasma is actually due to collisions of electrons with these ions. So with the ions that have already lost an electron, the collisions aren't violent enough to knock yet another electron off, but they are violent enough to basically send that ion into an excited energy state. These excited energy states are unstable. So they're going to these ions are going to spontaneously relax back into their ground state. In the process, they need to give off energy in the form of photons or light. The color of the light is dependent on the gas and the specific excitation process. So right now, I'm not using helium in here, I'm just using air. So this is an air plasma, and we get kind of this pinkish glow. Depending on the gas, we might be able to get reds or greens or the like. So another thing, if I set this just right, that you might be able to see is that we've got these striations that show up in the plasma. This is actually a kind of an interesting process. So remember, these collisions between electrons and ions occur after the electrons have been accelerated by the electric field. So what's happening here is that in one of these bright spots, there's been a violent collision between the electrons and the ions, enough to send the ions into the excited energy state. When that collision happens, the electrons lose energy. They slow down. And so they deposit all their energy into the ion, which gets excited and then emits light. It then takes, the electron needs to travel some amount of distance before it accelerates up to a high enough energy to be able to have this violent collision again. So you see bands of ionization and excitation, and then bands where the electrons haven't had enough time to speed up again before exciting an ion. As I stated earlier, one of the things that distinguishes a plasma from a standard gas is that this is a material where we've got freely flowing charged particles, so electrons and ions. And these can be the behavior of this plasma can be influenced then by the presence of electromagnetic fields. So what I've got is a bar magnet in my hand, and a pretty strong bar magnet. What I'm going to do is bring this in proximity of the plasma and watch what happens to striations. So I'm hoping that you can see that basically I am pushing the plasma around with this magnetic field. I just demonstrated to you that these plasmas do react quite strongly to the presence of magnetic field brought into its proximity. As I said, we can use this to our advantage. So one of the main driving forces behind the plasma physics research field is our push for fusion energy production. This is a nuclear process by which we can take the nuclei of two atoms, and if they collide with high enough energy, the nuclei will fuse and end up releasing energy in the process. So in order to get collisions that are violent enough to fuse these nuclei, we need to have a gas that's very, very hot, which means that we're going to be looking at plasmas. Additionally, we want to make sure that any energy that we add to these plasmas is not lost to the container, transferred to the container containing the plasma. We're going to use magnetic fields to accomplish this task. So imagine this is pointing along what's called a magnetic field line, indicating the direction of magnetic field. The charged particles, if you look closely at them, are going to be forced, the forces on them are going to force them to basically become trapped on these field lines and forced to orbit in kind of a helical motion along these fields. So they can move back and forth freely, but they can't move across the fields. They can't move perpendicular to the direction that the magnetic field is pointing. So if we have a nice, long, straight magnetic field, we can confine a particle, add energy to it, and get it very, very hot, and it won't collide with the wall. Unfortunately, we would need to have an infinitely long magnetic field and chamber to contain a plasma like that. So the trick we're going to do is take a field like this, and we're going to bend it around. We're going to curve it into the shape of a donut, so that the starting point of the magnetic field line comes back and bites its own tail. So that now if we confine one of these charged particles onto this magnetic field line, it's going to orbit helically around that field line over and over again in this donut-shaped pattern, and never colliding with the wall because there is no end to this tube. It's a curved cylinder. So this is the idea of behind magnetic confinement, one of the two main research fields that are devoted to pursuing fusion energy production. Beyond fusion energy, plasma physics was also played a critical role back in the 1980s and 1990s in basically improving upon the efficiency and thus efficiency of production, and thus lowering the cost of production of semiconductor chips. So these processes ended up being very dirty. There was a lot of dust that was created, and this dust became charged. By understanding and treating this as a plasma and understanding the dynamics of these charged dust particles, we were able to control where they went, decrease contamination of chips that we produced, and thus severely reduce the cost of producing silicon chips, and thus the electric components, the cell phones, the computers that we use normally. So plasma physics is very much one of the things responsible for bringing costs down for consumer electronics. Beyond that, there's active research going on in using plasmas in the medical field and in the field of dentistry. So if you've ever gone to the dentist and had to have your tooth drilled, eventually that drill could be replaced by a plasma, a plasma at atmospheric pressures to basically cut out and sterilize decayed teeth. These plasmas can also be potentially used to sterilize skin and treat damaged skin while preserving the skin around it. And it's also been used quite commonly for sterilizing surfaces. If you want an ultra clean surface, plasmas can be the way to achieve that. Beyond making plasmas work for us, there's another reason for us to be very interested in the field of plasma physics. So some estimates place more than 99% of the visible matter in the universe to be in the plasma state. So, if we're looking at stars, if we're looking at nebula, if we're looking at interstellar gases, all of these are going to rely on plasma physics for developing an understanding of these items. While you may not see plasmas and interact with plasmas every day, they are around you all the time. You can look up at the sun, and that is a ball of plasma that is relying on nuclear fusion to produce energy that ends up being directed toward the Earth and keeping us warm and providing light to us. If you've ever seen the northern lights or the aurora, this relies very much on plasma physics processes. And these aurora have been observed not just at the north and south poles of the Earth, but also on other planets like Jupiter and Saturn. If you've seen lightning, we have ionized gas very localized in the right around where the lightning is occurring. And then just looking at a simple candle flame, we have a very dirty, a very poor plasma, but a plasma nonetheless. We are going to have some ionization of gas right in the middle of that candle flame. So even if you don't know it, plasmas are playing a pretty critical role in your everyday life. Hopefully, through this introduction to plasma physics, I've helped teach you a little bit about what plasmas are, why they might be interesting, and how they can be useful to us. If you have any further questions about this, please feel free to reach out to me. If you have any other questions about our program, please reach out to anyone in the physics department here at Washington College, or reach out to an admissions officer who can put you in touch with the correct person to answer the questions that you have. Thanks for coming to learn about plasma physics, and I hope you enjoyed it.